for the world, and then we talked about, okay, but the world isn't as we hoped very often, because if the world had really matched that linear, there's still issues about how you deal with it when that happens, but it's possible to deal with it if your data is naturally low rank in that way. But what we're saying is our model, which is a function of inputs, and this is the real, when you're doing Gaussian processes, that's what you get excited about, seeing something that's a function of x, because that's where you put your prior. But for the moment, we're just saying that that's a fixed thing. So we're saying that f of x is mx plus c, and we set the mean to be that, and then we make our data predictions. For each data point, we say the mean of the Gaussian is given by the model, and then we sample either side of that with variance given by sigma squared. So we often write this down like that, and I think that that's what we all might sort of think of as a sort of regression model, that y is equal to some function of x plus some corrupting noise, and it's in this case we're saying that the noise is Gaussian. So that's a sort of a regression between x and y. This might be a regression between weight and height. So obviously the taller you are, the heavier you are, so you could maybe try and predict someone's height given their weight, and then you fit the best line. So in this case, what we're saying is that the likelihood of an individual, well, it should be the likelihood of the parameters is given by this function. So we've got two parameters in this system, or three, sorry, because we've got the noise as well, but two parameters in our model and one parameter in the bit that says how we depart from the model from the real world. Now, we talked about independence, and I think that this is very important. And this is something I want, hopefully by the end of this course, you're going to stop writing this down as a first objective every time you do something. Because actually, I think things are a bit more interesting when you drop this independence assumption. But the independence assumption will drop naturally, actually. People say, we'll make an IIG assumption. And I think that that's, what they really mean when they say that is they mean that the noise process is independent and identically distributed. If your data was totally independent and identically distributed, you wouldn't learn anything about it. The noise is independent and identically distributed. So what that means is that the multivariate distribution, and I believe in this way of doing things, if our data is y, we want a probability distribution over y. And if we're assuming that these noises are all sampled independently, then the probability over y is given by the product over the individual data points. Now, the nice thing in this case for the Gaussian distribution, so if we substitute, there's conditioning here, and that's very important actually. This is the bit that I think people forget. If there were no conditioning, then this model is just saying things are totally independent. So we might have a model of height that said that your height had a mean of 1.7 meters and a variance of whatever, 0.02. And then we sample heights independently, right? But heights aren't independent totally, because if you know things about sex and weight, they start to correlate with each other. So marginally they're independent under this model, but this model, when we're modeling in machine learning statistics, we're very often putting extra bits in. So what we're saying is that they're independent given the input location and the gradient and C. So the model isn't overall saying these things are independent, because if you're not given these things, then you get correlations appearing. So if you look jointly at the data, then you would find there are correlations across y. Yeah? So if we plotted everyone's height, we would find there was some sort of correlations, and the reason is what we're trying to do in the model, though, is find things to condition on that make those things independent. Substituting in the Gaussian, we get a structure like this. And then we can use these nice properties of exponentials, that the product of a series of exponentials is just the exponent of the sum. So that product sign just sort of can be put inside the top there. You see what I'm doing there? It's just jumping up into the exponent, becoming a sum, and leaving behind an n over 2 in here. So this is the likelihood of our data. Now normally we don't work directly with the likelihood, we work with the log likelihood. Why do we do that? Well, there may be a few different justifications. One reason is because we can. If we're going to maximize the likelihood, which is the typical thing we do, it's the same equivalent to maximizing the log likelihood. Another reason is convenience. Something that involved a product here, because we take the log, now involves a sum. And if we're going to optimize, we normally have to do derivatives. And if we're doing derivatives, those derivatives normally work better if we're working with sums rather than products. It's also got interpretations, information theoretic interpretations, but it's just traditional to work with the log likelihood. So the log likelihood is giving us the probability of the data given our parameters. And what we know about it is that if the data was really generated according to the probability we specified, then we could show this thing's consistent, that the correct parameters would be recovered in the limit as n goes to infinity. So if someone really generated the data set we're given by taking a linear model with a parameter m and a parameter c, and they added Gaussian noise to each sample, what you can show is that as the number of samples you're given goes to infinity, you will recover the correct parameters. And I'm not sure if I don't think I'm going to cover that. Because to a large extent, I don't care. I mean, it's important, but no one ever gives you infinite data. And you pretty much never have the right model. So neither of these things ever apply. But this is the consistency of maximum likelihood that everyone talks about, that says that if I get enough data, I will recover the correct parameters. It's driven by the idea that the world has a probability distribution, sort of P of y. Well, it's, we'll call, and we're trying to model our model, we're now going to call Q of y. Now the KL divergence between these two densities is given by this dy. I may have the sign the wrong way around. I do. It should be minus that plus Q of y. Now this is a nice quantity. It's asymmetric, which some people don't like, but it's got all sorts of interpretations in terms of information theory. It's a measure of information divergence between the distribution. I've done that the wrong way around. Sorry, I did have the signs right. P there. So P is, in this model here, if I may have the signs the wrong way around. It's not really relevant to the discussion I want to give. If P of y is the real world that's given us the data, so the assumption here is someone's generating data in the real world according to Py, and we're trying to approximate it with Q of y. The KL divergence has a minima of 0, and it's 0 only if P of y is equal to Q of y. It can also be written, one way of writing it, this thing here, because that expectation is just over the log, is as this ratio here. So one way of seeing that is if this ratio, if these were matching each other, this ratio would be equal to 1 everywhere. So it's log of 1 everywhere, regardless of what P of y is. I can't quite prove to you that, well, I'm not going to prove to you that it never goes negative. But the point in this distribution is, and the point in writing it down in those two parts, is that we don't know P of y, but we do have our model for Q of y. This is our Gaussian model. But what we can try and do is we can use a sample-based approximation to this system. So the sample-based approximation says that this is approximately equal to 1 over n log q of yi sum over I equals 1 to n, where yi are samples from p of y. So this is a sample, this is how we do in statistics and probability. This is just saying that this is the expectation of log of q of y, and the true expectation is approximated by this sum, by the law of large numbers. That sum converges to be exact as you take n to infinity. And as we talked about before, this is making an assumption that these y's are being sampled independently. Now that approximates the first term. This second term you can't do anything with. But it's not dependent on our model. It's only dependent, it's the entropy of the real world. Yeah? So we don't know what the entropy of the real world is. So we're left with this term. And this term, if you bring the sum in here, product I equals 1 to n, is the log likelihood of our data. So in rough terms, that's the proof of maximum likely consistency. It turns out that maximizing this likelihood, of course, minimizes this negative term here, and therefore minimizes this KL divergence. So there's an information theoretic interpretation to what we're doing. I often find it not so useful because I can't do this. I mean, there's actually, you have to go to different proofs if this distribution isn't independent over y. Because this trick of pulling the sum inside the log only works if you're making an independence assumption on your likelihood. And I'd like us to move away from those sort of independence assumptions. So it gives you the proof in terms of KL divergences, and people keep referring to this, and more bizarrely, they refer to this as the correct KL divergence because it's the one that leads to maximum likelihood, which is a bizarre circular argument. Because you chose a KL divergence to prove maximum likelihood, and then you say this is the correct KL divergence. Because there's two KL divergences, right? The other one is Q of y, P of y, Q of y, Q of y. So for this KL divergence, we take the expectations of the real world under our model. But you can't compute this sample-based approximation. It's just not mathematically possible. Because you can't deal with this in a sample-based approximation. You can often compute the entropy of your model. So it would, of course, if you could do it, lead to also a consistent model. But it's just the KL divergence the other way around. And I don't like the fact that people bias towards the KL divergence that leads to maximum likelihood. So in some sense, I'm not super keen on that proof, although it is there, and it's another reason why we might do maximum likelihood. So that does lead to, because we're actually trying to minimize the KL divergence, there's a minus sign here. So we're trying to minimize the negative log likelihood. And very often what we do in optimization, it's traditional to minimize rather than maximize. So we'd like to the idea of maximizing probabilities, but there's an entire community of people that work in optimization, and they had to make a decision whether to try and talk about maximizing benefit or minimizing cost. Not for any particular reason. They just, it's like driving on the left-hand side of the road or the right-hand side of the road. Of course, it's correct to drive on the left-hand side of the road, and everyone should have done. But, it's arbitrary, right? You just have to make a decision whether minimize or maximize. And in optimization, they made the decision to minimize. So whenever you talk about things in optimization, you talk about convex optimization, meaning that you've got a global minima. If you were talking about maximization, you would talk about concave optimization. But that makes no sense in the fact that we're minimizing. So we're going to do that here as well. So rather than maximizing the likelihood, we'll minimize the negative log likelihood. But that also has this interpretation of minimizing this KL divergence. So people talk about error functions in machine learning. And these error functions match to, in the probabilistic interpretation, negative log likelihoods. So minimizing an error function is equivalent to maximizing the log likelihood. And the probabilistic interpretation that minimizing an error function is equivalent to maximum likelihood with respect to the parameters. So in the case of the model we've just talked about, there's two components to this error function. One is very often ignored. And the fact that people ignore that error function, we'll see when you get to Gaussian processes, explains why in kernel methods, people are unable to fit kernel parameters because they ignore that term in the error function. This is normally what we might think of as the least squares error function, just this quadratic part on the right, yeah? So this just says, when we get to this point here, we take the negative log of that likelihood, we're just left with the sum of squares error. Now I always forget, I think it's Legendre that proposed this for fitting models, published it before Gauss published his probabilistic interpretation, but Gauss claimed he had his probabilistic interpretation earlier. There was a priority argument. But this became a very popular objective function to minimize. Now, I just want to pause and think about it. If you make an I hate it. Well, I don't hate it. I shouldn't be too strong. I should couch my terms when I'm on video. I think it's a bad thing to interpret this as a cost function. Could anyone tell me when they have ever had to pay a quadratic penalty for missing a deadline or a flight or anything else? So let's say that you are running a shop and you have to predict how many bags of coffee, well, coffee doesn't really spoil, let's think of something, how many oranges to buy, because you're doing fresh squeezed orange juice, and you want to know the demand of the people to come in for the fresh squeezed orange. Right? If you underpredict the demand, you'll typically pay a cost in terms linear in the number you've underpredicted, because you've got a missed opportunity to make profit on each orange. Yeah? So if you have to close your shop at 2 o'clock because you've run out of oranges and there's still a queue of people, basically you pay a sum of the people you've missed. That's a linear cost, an absolute value cost, yeah? If you overpredict, if you buy too many oranges and they spoil, the same thing happens. You pay a cost associated with how many oranges you bought. So this is what we're sort of looking at here. This is the demand for oranges, and this was your model, what it said, right? Now, if we look at this in terms of paying money for mispredicting, you would not be paying a quadratic cost, yeah? So the form of this cost function is something like, here's the 0, and here we're paying a quadratic cost. So actual demand for oranges is higher than we predicted, and then we pay an amount that goes quadratically versus the difference between the oranges we wrote down as demand. What I'm arguing is actually for a cost like that, the true cost would be linear, I would say. But it's more likely, I think it's more likely to be something like linear than quadratic. And then maybe linear, but with perhaps a different gradient, going the other direction. So this is you underpredict the demand, and this is you overpredict the demand. Oh, sorry, it's the other way around, isn't it? I think this is the overpredict the demand, and that's you underpredict the demand. Doesn't really matter for the point. The cost, the actual cost that you're paying, is linear in the difference between the truth and what you suggested. Yeah? I have not thought of any example where you would actually pay a quadratic amount of money or a quadratic amount of disbenefit for your poor prediction. I can't think of one. It seems to me nonsensical. So minimizing the sum of squared errors, I don't think has a sensible interpretation as an empirical cost. Now there's question marks over empirical risk minimization, but I think when you see it, it's better to always think, this is now an objective function that we're going to try and minimize, yeah? But what I said earlier is there's two types of machine learning. One where you write down an objective function at the beginning and try and minimize it, saying this is our cost, and we're going to try and minimize our cost. And another way you try and write down the model. Now these things get confused at this point, because people sort of say, oh well, if we pay a cost which is our log likelihood, I don't think that makes much sense. I think that's confusing two different approaches, personally. I think one needs to be clear about what you're doing, and I think personally, and this is a personal opinion, you know, other people might disagree, and I can't prove that I'm right, that it's kind of a bit nonsensical to suggest you're paying a quadratic cost for mispredicting. So when I see that, I always think Gaussian errors. I don't think I'm paying a quadratic cost. But there are people who say this is a cost function or an error. You know, it's more explicit. If you say error function, I think error is either negative log likelihood or cost or whatever. We're not specifying what the interpretation of the error function is. That's why I use it as error function, not cost function. Cost seems to imply money's involved or some kind of penalty being paid. And I think that that confuses decision theory with modeling when people use this cost. Any sort of questions there? Because I know that's normally the way you start doing regression, isn't it? You don't have that term, but you're told, okay, let's minimize this. No one says why you should do it, or what the interpretation of doing it is, or how things could go wrong, because they didn't tell you what the model was. They haven't even told you what the algorithm is yet. There's something of the model in the cost function, but it's not all there. Questions? Okay. So we're going to try and minimize this. So, of course, I'm just going to ignore sigma squared. We could minimize with respect to sigma squared. But I want to focus on M and C and just use this to sort of teach a little bit of a lesson about an algorithm called coordinate descent and emphasize. I'm assuming everyone's pretty happy. People have done linear algebra courses, right? Have they? Yeah? Some raised eyebrows. Everyone, I mean, I don't know, in the UK now, it just seems that no one even knows what a determinant is, and they get to, it's just depressing. I was accused in my recent exam by some people of not relying on basic linear algebra, and all I relied on was matrix multiplication and determinants and matrix inverse. I thought I learned that when I was 16, but still. There's one thing is to, I suppose, having said that, I don't think I was ever given a physical intuition of the linear algebra and why it was useful. And I'm going to try and do that as I go through these derivations. So the sum of squares error function, and it's commonly used, and we want to now minimize it. So to minimize, we typically look for gradients. So we're looking, this is a standard sort of also, I don't know where it's taught in Columbia, but once upon a time it was taught in high school maths in the UK. If you're looking for the minima of a one-dimensional function, you're also looking for the zero crossing point of its gradient. So you're solving for the roots of the gradient. Yeah? So people are aware of that when they're doing root finding things. Now, the gradient of the error function with respect to m is given by this, and all we want to do is solve for the root of that equation. Now, why was least squares popular? Because that's now a linear equation. So you're sort of done. So this is why it was, when Legendre proposed it as something to minimize, everyone thought it was a good thing to minimize because it actually makes the maths really, really easy. And that actually explains its initial popularity. All the theoretical proofs about when it's a good thing to do came later. Having said that, and of course there are times when it's not the right thing to do, because we can show that there are times when the model is incorrect. We spend a lot of time talking about the model. The same thing is going to apply for Gaussian processes. This thing of the fact that the log of the model is a quadratic form, whether it's a multivariate or univariate quadratic form, it doesn't matter. It means that the maths is linear systems, linear algebra as a result. And it means we can compute all these things very quickly on digital computers. And there's other motivations also. So that's great. That's already a motivation for using Gaussian processes, that the maths, the underlying maths, can be computed very quickly. And then there's also other theoretical reasons. So it's very similar to the situation they faced back then. But we are interested in using these processes both for the modeling reasons and the algorithmic reasons. And we shouldn't get too confused. We shouldn't start confusing them, which Gauss actually did confuse this when he suggested the Gaussian density as the underlying model. So solving that solving that linear equation just gives us this update for m. So if we know c, so it's solved in terms of c, we can solve for m with that little update there. We can also do coordinate ascent on c, and we recover the same thing. Now the c one's a little bit more interpretable. C is given by the sum of all the observed yi's minus what our model predicts for them. So this is just like the mean of our residuals is given by c. That kind of is quite interpretable. I think the update for m is less interpretable. You're going to use this as a little exercise in the IPython notebook. Just get familiar with Python and for loops and stuff like this later on. So you're just going to implement this. But I like it because it leads to this series of fixed point updates that given m you can update c, given c you can update m, and then given m and c you can update sigma squared. These updates happen to not depend on sigma squared at all, just because of the way the maths drops out. Now that's fine, and what we then do in practice is we choose an initial value for m and c, and then given the value for which way are we going to do it, we're starting with, I should have plotted the starting point, but the starting point's here. So we're starting for m being equal to 0 and c equals to 1.5, and then we're updating m. Now this quadratic is actually a two-dimensional penalty surface because it's a quadratic that depends on two parameters, m and c. And what I'm showing, well, sorry, let's go back and show that in the error function. It's a quadratic surface that has m and c as parameters, and y and x are given. So what I'm showing on that surface is a plot of this, sorry, that should be m comma c there, a plot of this surface as a function of m and c given a data set y and x. Yeah? Makes sense? But when I optimize with respect to m, given c, I'm actually minimizing a one-dimensional quadratic. That's what I'm solving when I just minimize with respect to m. So that just takes me to the minima on that plane. And then I can now do my update with respect to c. So these equations here, this is solving for the root of the quadratic with m fixed. This is solving for the root of the quadratic with c fixed. And what we're suggesting is iterating between those two. Now this turns out to be really bad in practice. Really, really slow. This is the optimization running, and in order to make this visible, I've actually taken a data set with very few data observations in, because otherwise this would collapse down upon itself and there would be many, many more iterations. Even for the data set you're going to look at, the Olympics data, this error surface is much, much tighter. And you're going to find you take thousands of iterations of these optimizations to get anywhere near the minimum. Look at how it's getting smaller and smaller. Oh, it's a nightmare. So often you even converge, or you think you've converged when you haven't even converged, to some sort of minima down here, which actually looking at that point there, 1.05 and 0.35, is probably not. No, I don't want to go back through that. It's probably not even the minima. It's probably converging up here somewhere. It goes so slow by the end, these two different optimizations. And the reason is because these parameters are strongly correlated. They induce correlations in this error function. That knowing if you fix c, m is highly dependent on where you fixed c. Because if you fix c at 0 for time 0, you basically are constraining, in that Olympics example, you're constraining m to very stupid solutions. So this was the Olympics example. And if all the way over here, at year 0, you fix c to 0, you have to basically, you're saying that the line goes through here and you get only the choice of gradient. And all you'll do is you'll put the gradient through the data like that. And then given that gradient, if that's now the fixed gradient, you need to update c. It will go, oh yeah, c is too low. Let me update c. And this is what's going on, because these two things are very correlated. At each iteration, you're just getting updates like that. And it takes a long time to get to what the optimum is, which is a very large C and a negative gradient. So by starting with a bad initialization, well, and it's very easy to get bad initializations. If either of the parameters is some distance away from the truth, you get a bad initialization. And what's going on is you end up zigzagging down this valley for ages, because you're not allowed to get towards, you're not allowed to make a big jump towards the true value. Now, you should never optimize things like this in practice. And what linear algebra does is, in effect, it allows you to rotate the system where you're optimizing. So if these things were uncorrelated, optimizing in this way would be trivial. So if M and C, if the real surface was like this, right? So they're uncorrelated, then it doesn't matter where you start, one update would take you there, and the next update would take you there. If they were uncorrelated, you would be there in 2 steps. And my interpretation of what's going on in linear algebra systems, when you start using matrix systems, you basically have the ability to rotate bases. So you can take a correlated system like this and say, well, why shall I work with M and C? Let me just rotate the whole thing and work with a new basis like this, and then I can get there in 1 step, pretty much. I mean, that's my intuition about why linear algebra is so important and how much time it saves you to use it. We'll come back to that when we look at quadratic forms are very closely related to multivariate Gaussian densities, and the things that apply to quadratic forms also apply to multivariate Gaussian densities. But we'll explore that in more detail when we look at multivariate Gaussian densities. Okay, so second order methods are not things we're going to recover here. So if this is a quadratic system, so we can solve it very efficiently. We are going to make use of in the code things like conjugate gradient and quasi-Newton methods, which take account of the shape of the surface, effective heuristics such as momentum when people do gradient descent, local versus global solutions. These are all really, really important concepts in optimization that we're not going to talk about at all, because we're going to be focusing on these sort of quadratic surfaces. But they are implemented, some of these things, in things like GPy for optimizing kernel parameters when we get to that. Okay, so here's the optimized linear regression for those male marathon times. So it kind of looks like the best fit line, yeah? But I wouldn't be that satisfied with trying to make a prediction of the next marathon's going to be run in that's probably like an hour and 45 minutes or something. I bet that's wrong, and I bet the apostles could run a bit faster than whatever's proposed going back there. So I find this solution fairly unsatisfactory, and it's unsatisfactory for a few reasons. It's the wrong model. We've just got one proposed solution. We're not seeing anything about, can we show anything about error bars? We could show the variances, and the variances would just be a tube down like this. And that's sort of what we get from the maximum likelihood solution. So I would say that it's quite likely. Okay, to be honest, I think if you were really processing this data, and I won't go too much into the details of this, I think the first thing you should do is take the logarithm of these times. And then maybe you'll get something a bit better, because a log linear model would be more like that you expect a consistent percentage improvement year on year, which is the sort of thing you might expect with times. So, I'm not really showing that side of it because I like the nonlinearity here. But part of this nonlinearity is if there's a 95% improvement year on year, right, then you will just get a shape like that, a sort of geometric progression, yeah? And if you want to model that with a linear model, the thing to do is take the log of that and then that multiplicative effect becomes an additive effect, and then you'll get a fit that's broadly speaking like that. So I haven't done it, but that'll be an exercise now, I've decided, in the lab class, to just take the log and fit the log of the times rather than the actual times. Be aware, be always suspicious if you're fitting Gaussian densities to positive numbers. Times are positive, yeah, they can't really go negative unless you're looking at differences. So if you know your number's positive, just have a sanity check saying, do I really think it's Gaussian? Because Gaussians sustain negative numbers, right? This is going, in the future, it predicts we'll run marathons in negative time. Now, one way you can prevent that, and it's often a sensible thing to do, is to take the log, and then it will sort of decay away. And if you do that, then your interpretation is, instead of each year a fixed improvement in time, it's a geometric interpretation of each year a multiplicative improvement in time, which is more sensible, I'd say, that, you know, humans, if we are getting better, we get better with some percentage rate. So that's just a side comment, but we don't do it this, because actually I want the wrong fit. So let's say we didn't have that type of knowledge, and what we really wanted to do is model nonlinear relationships between our data, our observations and the data. And in fact, this is, if you think about planetary orbits and Kepler's laws, they are nonlinear in the sense of, if you look at the planet, it doesn't go in a straight line all over the place. What you do is you come up with a set of basis functions, and the idea of these basis functions is that they create a space in which your regression is linear again. So the basis functions for modeling planets are ellipses. So combination sums of different ellipses, sinusoids and cosines, can sum together to get the right planetary orbit according to Kepler's laws. But in general, we could use any set of basis functions we like. And what we do is we keep our model linear, in some sense. We keep it linear. It's non-linear as a function of x, but it's linear as a function of the parameters. So this is a slight confusion. You're still sort of using the class of linear models, but the functions you can get are non-linear. And Gaussian processes are an example of that. So if you're used to, you know, when I first came into machine learning, with my simplistic point of view, I would have said Gaussian processes are non-linear models because they represent non-linear functions. But in terms of the algebraically, the maths, they're very much linear models. You can do everything with linear algebra, broadly speaking. So basis functions can be global. So what we're trying to do is say that our function now, our view of the world, is equal to a weighted sum of some underlying functions. So those might be global functions. So if we just took these two, we would be doing exactly what we were doing before. A weighted sum of a offset and something with a gradient, yeah? So the interpretation of weighting this is changing the gradient of the function. The interpretation of weighting this is changing the point at which it goes through the zero, the intercept. But we can now add perhaps another basis, a quadratic term, which is like the curvature of the function as well, we're adding in. This no longer has the interpretation of the gradient because that affects the gradient. But this does have the interpretation of being the curvature. So you can sort of sum those three together. So here's some different weightings. So in this case, we've taken a weighting of the constant thing of 0.87. So that's being weighted by 0.87. That's being weighted by minus 0.388. That's the linear term, this basis function here. And this is by minus 2. So what we see is the sum of those three things is at 0, we go through something that's 0.877. Yeah? We then have a sort of skew to our quadratic, which is so it's not symmetric about 0 because we've got this small negative average gradient or something. I don't know what it is. And then we've got this curvature coming from this minus 2. So that blue line is the sum of these three basis functions weighted in that way. And we can do a couple of other bases. So there, the curvature is much smaller, and the linear term is positive. So on and so forth. We can also consider things like these Gaussian bumps as basis functions. So here's a different set of basis functions, and these are sort of local bases. So with local basis, we can add these together, and depending on the weight, so here this one's heavily negative weighted, minus 1.81. This one's slightly negative weighted, and this one's more negative weighted. So you can see you get this sort of bumpy effect for giving you a nonlinear function. So here our f has this form. It's still linear in the parameters, w3, w2, w1. As long as we don't take these basis centers as parameters, it's linear in the parameters. And we can sum different sets. Of course, this also relates to multivariate regressions. So what we're getting now, if we had a multivariate regression where we've got several different inputs to predict the same thing, so we've got spectral inputs, for example, in that meat measurement, we've got like the spectral response in one bandwidth, the second bandwidth, and the third bandwidth. We've got these three different inputs. You can also see that as a basis, right? So we just have this form, the sum of some weighting of those inputs being equal to our regression. So these basis function models just take us into this domain of multivariate regression. So this could be seen as mapping our original one-dimensional input into a new three-dimensional feature space. I don't know what the spectral measurements are saying about the meat, but they are in some sense a basis of some other measurement one would be able to make. So these two things are really in some sense one different type of model where we're summing either the original data or some transformation of the original data or some nonlinear mapping of the original data, and then we might be adding an offset, but in general we can combine that offset in here. Now this is the point at which I think it's so important to go to linear algebra. A lot of people apparently disagree with me because you'll see formulae like this all over the machine learning literature. But I just think that the linear algebraic representation is much, much more powerful for derivations. And I don't know how familiar people are. I mean, that's just an inner product, right? So it's just a weighted linear sum of those things. And you just need to get it in your head that that's all that is, that it's nothing complicated. And then this representation is much more powerful. It requires less ink as well, which has to be a good thing with the cost of printer ink. It just seems to be a much more natural representation. Now, of course, we can go through the same process as before, but now we've got this slightly more general representation where we're using x here just so there's less Greek letters in it. But I could put phi here to be the bases instead, because Greek letters make things slightly more complicated. But equally phi or x. Here's our likelihood for either a multivariate regression or a system of basis functions. Now, if we look at this and treat it in the same way as before, then we can just get this sum appearing as we take the product and then the log. We get this sum appearing up here, and then we get an error function of this form. It's kind of obvious because all we're doing is substituting our f of x for w transpose x. Sorry, I skipped through this one little step here, which said we never bother writing the c outside because we could always think of adding a basis function to deal with c. So that, in this representation, means having an x0, which is always the constant value. But this is now our representation of f of x. It's just an inner product between our data points and some weights, or the features of our data points and some weights. And this is just the substitution of that f of x into what we looked at before. Now, the only complicated thing in this expansion here is knowing how to write the square of this. So all I'm doing there is expanding the quadratic. So I'll write it as y minus f. I'm going to leave off the sum. There's really a sum in front of it as well. Y minus f squared, yeah? So if we expand the quadratic in this way, y squared minus 2fy plus f squared. Yeah, everyone agree? That's all I've done on the next slide. Only, there's also a sum on the outside, yeah? And this sum applies to both of these terms, in effect. So you get a sum of yi squared, a sum of two fi yi's, and a sum of fi squared. Yeah? And now, further trick. When you write this down, it took me, I don't know, I really drum this into my master students, and they still get it wrong. That f is basically this, yeah? So what we're saying is that f squared is really that. But you need to learn to write that in a special way. That's a correct way of writing that. But if you write it in that way, you don't see the matrix forms emerging. The magical matrix forms emerge when you write it in one of two ways. Like that, which is actually the wrong way for this case, because you still can't sum over these two guys. They're sort of on the outside. It's not obvious where the matrix appears. Or, I mean, all that is just that, right? So that's clearly correct. Here's one that was never, I don't know what the use of writing it like this would be. I can't interpret that. So there's four ways of writing it or something, and the one that's really useful is to write it like this. Because now when you take the sum can push through the w. It's just like integrals as well. You always want to make it so that you can write it in the simplest way, not integrate over things you don't need to integrate over. So now you've got a w transpose sum of xi transpose w. Now you can realize that that guy in there is a matrix on its own. Yeah? So having just shown you on the board, that's all I'm writing down here. So I'm just choosing, I've also got the scalings in here, and the log sigma squared. And I'm dropping the constant that's to do with 2 pi. But everything else, there's the y squared, there's the yi fi, there's the fi squared. Yeah? But then the trick is to pull that in and notice that you've got this matrix form. Now what you've got is a multivariate quadratic form. Indeed, it is the quadratic form that I plotted for the optimization example earlier. So this guy here dictates that correlation structure of that quadratic. If this guy was a diagonal matrix, remember I said, oh look, we've got this remember I said, oh, we've got now this horrible sort of ugly correlation thing like that. That basis there is actually the square root of this matrix, the matrix square root. So we'll see if you do that as an eigenvalue decomposition, the eigenvectors of that matrix lead us to this basis. So that's the nasty mean guy that causes the correlation. And he's just dependent on x. He's not dependent on y at all. The mean is actually dependent on that and this, which is dependent on y. So this correlation structure, you even know before you observe the data that you've got it in the linear system. And it's entirely driven by your basis. It's not driven by your y at all. So the y just shifts the center of this optima around the space. But basically, it's in your x's, this correlation structure, for this example. So this is, I mean, because this quadratic form is that error surface we were optimizing earlier, only in this case, we're sort of putting w is equal to m and c. And x, each xi is equal to sort of whatever the original xi was, the time, and the constant vector. So this guy here is just the sum of the outer product of all the times and a bunch of ones. Make sense? Now, the nice thing about that form is it's just a quadratic form. And these multivariate derivatives can be used to solve it very, very quickly. So simple multivariate differentiation, I mean, you can think about these rules and why they're true, but in multivariate differentiation, it's just a variant of partial differentiation where the partial derivatives are put in a vector. So this is the derivative of the inner product with respect to the elements of w. So the partial derivative, this vector is each of the partial derivatives of that with respect to w1, w2, w3, w4, w5. And since the inner product is a1 times w1 plus a2 times w2, you just get the result A1, A2, 3, 4, 5. Yeah, that's the multivariate derivative of an inner product. Slightly more complicated and more difficult to explain is the multivariate derivative of this guy, a quadratic form. W transpose AW is actually very closely related to the linear one, so it's A plus A transpose W. If this was, sorry, linear one, the scalar one. If this was AW squared, this is equivalent to A times W, derivative of that, which is given to A, and this is the equivalent of the derivative of A times W squared, which is normally 2AW. But in the matrix form, it's A plus A transpose W, if A is asymmetric. But if A is symmetric, it's just 2AW. So it's just the multivariate version of these standard quadratic derivatives. And if we apply that here, we've just got W. If you want the gradient with respect to W, those terms do not depend on W. This term is linear in W, and its gradient is 1 over sigma squared times this guy here. Yeah? Because it's a linear term in W, and this is a quadratic term in W, so its gradient is 2 times 1 over 2 sigma squared, so 1 over sigma squared, times this guy here times W. This is that matrix A. So putting that together gives us, so actually, sorry, I've substituted beta for 1 over sigma squared. I shouldn't do that. We get this form here, and setting that to 0, finding the roots of that equation, that's our solution. Now this solution is nice because what actually happens is this guy is decorrelating everything. He's causing the system to become decorrelated so that you in effect are solving it in one shot. So this solution is a one-off solution because it's not dependent on anything apart from the data. Now that's not obvious that that's going to happen at the start, but because it could depend on the noise variance. And indeed, if we had a non-Gaussian noise, it would depend on this non-Gaussian noise in some sort of way. But in the Gaussian noise case, the noise cancels, and it just becomes dependent on the data. Now it becomes convenient, I think, to take these. We can see this vector notation has already got us somewhere. It's got us this system that we can now rotate and we can understand as a multivariate system. We're going to go even further. I don't like those sums either. I want to get rid of all these funny big sigma signs because they're confusing. And that can be written in this form here. If we use the standard in statistics, which is to write our data in the form of a design matrix. So a design matrix X just takes each of those feature vectors, x1 associated with the first data point, down to xn, and sort of transposes them and puts them in a matrix like that. I believe that's the right way to do it. Why do I? Some people like to write this the other way around. Why do I believe this is the right way to do it? It's the same as the optimization thing or which side of the road you drive on. The statisticians got there first, and they defined it like this, and it's confusing if everyone does it a different way. So let's just do it the way the statisticians do it. Some people do it the other way around, which I find annoying. I think they might do it the other way around in the book, because the problem is, if you know which way round it is, it becomes very easy to see what you're looking at. This turns out to be related to the covariance of the data. So if you think of this form here, and then you're multiplying x transpose by this form, what you actually end up with is a series of x1 to xn's pre-multiplying this, and that gives you x times x, x1 times x1, plus x2 times x2, so on and so forth. It's just like a matrix in a product. It allows us to write this sum as this multiplication of the design matrix. The other thing we need is also just like an inner product. This is just like a weighted sum of the input bases, and it's written if we define that the data observations. So this matrix can also sometimes be called phi, the feature matrix. It's the same thing, but it would be phi 1 down to phi n, where these are each of our basis vectors. Y, then we define as y1, y2, all the way down to yn. Yeah? That's our vector y, the multiplication of phi transpose times y, gives us this other object we need. This means it's a two-liner in anything that can do linear algebra. Yeah? Annoyingly, I will say that Python, I don't like the way Python has implemented matrix multiplication. So let's get annoyed by that at the beginning and then try and forget about it. In Python, it's done by np dot dot, which is a bit ugly. So maybe I'll show that after the break. We'll take another break in a second. So that means now that's the form of our update for W star in matrix form. So someone gives us a feature matrix or a set of inputs and a set of observation values, and then we need to do this. Now in practice you don't do that, because in practice you're solving a linear system. So you'll see in the lab class, I think, if I've done it right. So what you're doing there is really you're solving this system. Yeah, which I think the numerical analysis people would write as A times B is equal to X, is that right? Or AX equals B? AX equals B, I think. They solve for X, don't they? Yeah. So numerical analysis people would say you're solving this system where X is W, X transpose X is A, and X transpose Y is B. So this is done. You don't actually explicitly invert this and multiply it on that side as I've shown there. What you do is you ask the computer to solve this system of simultaneous equations. So we're back to simultaneous equation solving, but the simultaneous equations we solve aren't dependent in a sort of funny way on the data. We've got this sort of multiplying matrix there. So you didn't have before. You could also do it for the sigma squared. For the sigma squared, it's a slightly different result, and it doesn't involve really linear algebra at all. And it just comes out as the sigma squared is equal to the empirical variance of the data. Yi minus the prediction squared. This was the formula I hated as a schoolboy, so I still don't like it much. That's how you compute the variance of something if the mean is given by that. Yeah, if that's the mean, you subtract the mean for each data and compute the variance with the residuals. Okay, so what I think we'll do is we'll stop there for another break. Yeah, or questions first, and then a break. Yeah.
One question about the use of basis function. How we choose the number of basis functions?
Good. I'm going to answer that question later. I think that is so critical. So basis functions, what we're going to get to, I hope, is a point where you all understand it becomes all about the basis. That like if you look a load of the body of work.
The memory of the camera is full.
Ah, how do you know? On that camera?
Yeah.
Okay, well I think it's just feeding directly in anyway. It's more a worry about whether my... no, okay, I think well, hopefully that will be all right. Or you won't see me, which will be an advantage on the video. Okay, so the basis functions, I think at the end of the day, that's what it gets all down to. That you push this nonlinearity into this basis function set, and then everything starts to become about the basis functions, and then you have to think very carefully about your basis functions and what you want to say, and things become very dependent on that. When we get to Gaussian processes, what that means is it's dependent on the form of the covariance function you select, because they turn out to be equivalent. And the thing, so we have a Latin motto for the Gaussian process summer school, and it's really supposed to reflect that. But see if I've got the internet now. No, I still don't have it, and I don't remember it well enough. Oh, and it's on here. It says, all written in front of you. It says, Uditium posterium discispilus est prioris. Now, I don't know exactly what that means, even though I helped design it. So I like the fact that there's uncertainty in the meaning of the motto, because I think life's about uncertainty. But one of the things I want it to mean is model is king. And when I say model, I mean prior covariance, the basis functions. That you will not, what you get out of your data is dependent on what you put in on the model side. And that question about what the basis function should be, I think that's really, really important. the answer is totally dependent on the situation of modeling.
And the same question about what type of basis we can use. That is, we can use Fourier basis functions or splines or wavelets or...
Yeah. All those things are great, and in many, many cases they all turn out to be Gaussian process models. And one of the things I'm railing against is that it all becomes about the algorithm and not about the model. That when people are doing signal processing with band-limited functions, they are assuming a Gaussian process prior with a particular covariance function for their data. When they are applying a Kalman filter to data, they are assuming a Gaussian process prior with a particular covariance structure. If wavelets are being combined in a linear way, that's another Gaussian process prior. It's another basis function selection, which people are all finding important in different places. But actually they spend all their time talking about the algorithm. How do I fit the wavelets? How do I do the Fourier transform? They don't actually step back and say, what am I saying about the data and when's it going to go wrong? And the people who originally designed these algorithms used to talk about the models. Now Gaussian processes allow us to unify all those things back into the same class of models, along with Gauss-Markov random fields, you know, and a load of other stuff. And I think that they should be seen from that perspective, and then for a particular example where you feel that wavelet is appropriate or Fourier basis is appropriate because of your domain knowledge, then you start talking about the algorithm. But it's difficult to say in general what's appropriate when. But we know that we can use things like marginal likelihoods to help us. So if we use the modeling framework and we say, well, this is the marginal likelihood of a model which uses a Fourier basis, or this is a marginal likelihood of a model that uses a wavelet basis, and what's the degrees of freedom and all that other sort of stuff, we can start answering questions about which is the right approach, perhaps. Although I've not really worked so much in signal processing. Other questions?
Well, I thought you said that trying to invert directly X transpose X is kind of unwise. Maybe if you use a Gaussian prior over W, so you have like a plus Radial.
You're all running too far ahead. Yes.
I'm wondering if it's unwise too, or if it's okay to invert.
It's okay, but I think again now we're focusing on the algorithm. It will work algorithmically. It will always work to put a Gaussian prior on W. It will regularize that inverse. It ends up having an effect of adding a diagonal term to X transpose X. It won't necessarily solve the modeling problems that may be associated with the basis. So if that basis is giving us numerical challenges, it may be because of modeling issues. I mean, there's this odd parallel. And just adding that back in maybe gets us the algorithm working again, but may not be solving those modeling issues, and maybe we should be looking at another basis where that inverse wasn't stable. We can't do this solution of a numerical situation purely on its own when we do the Gaussian, the Bayesian example, because we need to solve determinants and other things. So it becomes a little bit harder to deal with. But yes, you're absolutely right, but then it's also a confusion when you say that. It's another confusion between model and algorithm, because you're offering a modeling solution for an algorithmic problem, which may be what we do in practice, but let's try and keep them separate in our minds. Yeah? But we're going to do that. Okay. Other questions? Okay, so let's break again for 10 minutes? 10 minutes, yeah. Because then we'll go to 12:30 and then finished, yeah? Okay, good. So 10-minute break. Yeah, the camera shouldn't actually be recording. It doesn't need to record. The camera doesn't need to record. It just needs to provide